Hello, everybody. My name's Adrian Bowyer, and I'm the person who created the RepRap project, which is what I shall be talking about today. Manufacturing for the masses. This is a possible way, where we can move the whole idea of making goods from centralized production to distributed production, ultimately to individual production, and it's the way in which we might progress from where the world is today to how that might happen that is the subject of my talk. Before I start, though, I'd just like to thank Eric and several other people in the audience, all of whom have been very helpful. Eric has set up his machines over there. My little machine is here. You'll notice that they're different. We'll come to that a bit later on. So thank you very much to them, and also thank you for the organizers for inviting me and for paying to put me on an airplane, which was very kind of them. Okay. Many of you know what the machine is, but just for some of you who don't, RepRap is a 3D printer. It's a machine that makes three-dimensional objects in plastic from description on the computer, completely automatically in plastic. But the key thing about RepRap is that it's a replicating 3D printer. It's been designed so that it can print its own parts. Not all of its own parts, as we shall see in a moment, but a significant quantity of its own parts. That's a picture of the machine on the screen there. That's the machine, in fact, a very similar machine to the one that you can see on the front bench there. And this little part here is that part that's on the screen over there, and that part of the machine is actually this bit of the machine down here. And so everything you can see on that picture that's this sort of silvery whitey color was printed in a machine like that one in order to make that one. So it copies itself, in part. A few facts about the machine. It can copy about half of its own parts. That is, if you don't count nuts and bolts. It's got lots of nuts and bolts in it. If you count nuts and bolts and then look at the pie chart, the entire machine is made from nothing but nuts and bolts. So if you discount fastenings, then it prints about half of its own parts. In fact, that's not really cheating, because it would be perfectly straightforward, if you wanted to have the machine print a series of little cylinders, which you could use in the place of nuts and bolts, and glue the parts together. That would work fine. It would just mean that you wouldn't be able to take the machine apart again, which, from the point of view of maintenance, is not such a clever idea. But in that way, it would actually be printing literally that half of its own parts. It was deliberately designed so that the bits that it can't make are very easy to obtain from hardware shops or from online stores. For example, these threaded rods here, they're M8 threaded rods, completely standard size. You can get those from a builder's merchant just down the road. These motors here, standard NEMA 17 stepper motors, they cost about 10 euros each. So everything in the machine that it can't make for itself has been designed to be as easily available as possible. And if you want to put one together, the cost of all the materials you need to put the machine together is about 350 euros. The working volume, the size of the object, the biggest object it could produce, is 200 by 200 by 140 millimeters. Now, that's effectively the region above this blue area here up to the height that the machine can build. It would take quite a while to make an object that big. One of the things about this technology is that the time it takes to make something is proportional to the volume of the object, and the volume of an object, as you all know, goes up as the cube of its linear dimensions. So if you double the size of something, it takes 8 times longer to print. One of the disadvantages of this technology, but we'll come to that a little bit later on. It'll build objects in most thermoplastics. That's plastics that melt and then re-solidify. But the two ones that we use most of all are ABS, which Eric has on that yellow reel over there. That's ABS, I think, Eric, is it? Yeah. That's one of the plastics we use, which works quite well. But the very best plastic that we found to run in the machine is the plastic that this machine is made from. It's this stuff, which is polylactic acid. And I'll say a few more words about that later on. It prints at a rate of about 19 milliliters per hour, which means that to copy all the parts of the machine that it can print for itself, the machine takes about 2.5 days, though that's getting faster all the time. And finally, and perhaps as important as all of those other facts put together, is the fact that it's licensed under the GPL and it's distributed free, both as in freedom and as in beer, on the web for anyone to download. And the GPL, of course, means that anybody who makes improvements in the design also has to distribute those under the GPL, as you all know even better than I do, which means that the design can evolve, and those evolving steps are always going to be available under the GPL. Here's a little map. When people start putting machines together, we invite them to put a pin on the Google map. This is by no means all of the people involved in building these machines, but these are just the ones who could be bothered to put a pin on the map. But it gives you an idea of the distribution. Unsurprisingly, Europe and North America have pretty dense populations, but they're starting to appear in South America, Africa, Eastern Asia, and of course there's another concentration in Australia and New Zealand. That's a snapshot about 2 months ago, just to give you a rough idea of where everybody is. The total number of people building machines, we don't know, because it's on the web, anyone can download it. I keep discovering people who built machines whom I've never heard of. So we have no real way of estimating, but the best guess we've got is about 2,500 RepRap machines and RepRap derivatives. That's to say machines that people have designed based on the RepRap ideas, but have either made or sold that are not quite the same design as RepRap. What sort of things does it make? Well, one of the guys on the project, Zach Smith, set up a website called Thingiverse, where people can upload designs for objects to be printed, and then anybody can download them. And to make this slide, I just went to Thingiverse, clicked on the RepRap link, and that pulls up everything that's been tagged with a RepRap tag, and selected 6 things at random. And it's a pretty versatile device. So top left, we've got the drain for a shower tray. Somebody cracked the drain in their shower tray, and they didn't want to go to the shop and buy one, so they just had their machine print one. Sticking with a bathroom theme, in the middle at the top, there's a stop for the shower door. Not the same guy, I don't think, but that was printed in the RepRap machine with a little cork insert for where the glass just touches it, to stop the door smashing against the wall. Top right, we've got a series of little interlocking trays with drawers, so that you can build up a stack of these things in order to put resistors and transistors, chips and so on in, or indeed any small components, or maybe a spice rack. Bottom left, we've got a series of eccentrically and interestingly shaped containers that have been sprayed gold. In the middle, at the bottom, we've got a Saris linkage. Oh, Eric's got one over there. Thank you, Eric. In the middle, at the bottom, we've got a Saris linkage. The way the machine works, and I'll be running it after my talk, the parts and components of the machine move around in Cartesian coordinates on these sliding rods. Those that are part of the machine have to be brought in. The person who designed this linkage is trying to eliminate those by making a parallel motion, which is almost entirely designed in the machine and built in the machine itself. This is a parallel motion that doesn't require sliding rods. It just requires hinge joints, which are here, here, and here, and so on around the object. So that is a far higher proportion of self-printed parts. And bottom right, we've got a little robot. Might be an educational toy, something of that nature. All the mechanical components that decide the geometry of the robot were printed out in a RepRap machine. And that's just a sample that I took. We'll see a few more things that the machine makes a little bit later on. Now, but the key point, as I mentioned, is that the machine is capable of printing out a significant fraction of its own parts, which means that any one of you, ladies and gentlemen, who've got one, can print out another one for a friend. And because it's free under the GPL, you don't have to pay any license fees, of course. You just give it to your friend, and then your friend has the ability to print out all those objects that we saw on the previous slide, and lots of other things beside. This is actually the very first time that the machine copied itself. That's me on the left with a slightly projecting stomach and the balding head. And the chap on the right with the ponytail is Vic Oliver, who's another one of the guys on the core team of the project from New Zealand. His was one of the lollipops on New Zealand that you saw on the map earlier. The machine on the left is the first machine that we made, and you'll see it looks like Eric's machines over there. That's version 1 of the RepRap machine. That machine, of course, there was no RepRap machine to make its parts, so we made the parts for that on a commercial 3D printer. And then that machine on the left made the parts for the machine on the right, and that machine on the right was assembled, and it made, that's the parent machine on the left, the child machine on the right. The machine on the right made its first grandchild part on the 29th of May, 2008. And in fact, the first part that the machine on the right made was a part for itself. And the reason was this. You'll notice that there's this chain that runs around here that drives the vertical movement of the 3 coordinate directions. When we put the thing together, we discovered we'd made that chain a little bit too long, so it was too slack. And so the machine didn't work properly because the vertical movement wasn't being driven properly. However, we could make it work properly simply by holding a screwdriver against it to give it a bit of tension. So what we did was we designed a little cable tensioner, which is over here, and we then had the machine make that while we held the screwdriver onto it so that it could make it, and then we fitted it to the machine, and then the machine worked. So not only can it copy itself, it can also implicitly, when you've got a machine that copies itself, it can repair itself. So all this is really like MP3 music sharing, but for real solid stuff. Here's another thing from Thingiverse. That's a pan and tilt camera mount, webcam mount, made in the machine. And though at the moment the machine only works in plastics, we're moving towards having it work with lots of other materials and improving the precision. Again, I'll say a little bit more about this later on. Ultimately, there's no reason why it shouldn't make any stuff. It'll be a long time before people use it to make super tankers for shipping all around the world. It'll be rather less time before people are using it to make the equivalent of an iPod. Okay, now this is the point where I just start pontificating and waving my arms about. And so if you feel like disagreeing with anything I say, please heckle. It makes things so much more interesting. This is, I contend, how the world works. There are basically 4 levels of activity in the world, 4 levels of constraints on what people do. And these levels, as you go up higher and higher, from 1 to 4, each level trumps the level below. Each level completely dominates the level below. At the bottom level, there are rules. Things like, you must not eat pork, or here you must not drive faster than 50 kilometers an hour. And those rules are essentially things written down on pieces of paper by a human being or a group of human beings in the hope, sometimes backed up by main force, that other human beings will do what those rules say. And, of course, society extracts sanctions for people who break the rules. If you rob a bank, you go to jail for 10 years. If you marry someone outside your religion, you get executed. It's the type of punishment you get sometimes fits the crime, sometimes it doesn't. But we've got that entire system, and that system runs at all sorts of different levels. If you're a member of a sports club and you cheat at the sport, you've certainly not committed a crime, but it may well be that the opprobrium which falls upon your head as a consequence of the disapproval of all your friends is far worse than going to jail. And that's the way that human society works at that level. Above the level of the rules is the level of money. And almost always, money will trump the rules or make the rules change in order to fit the money. As an example, in almost everywhere on Earth, it's against the rules to ingest the alkaloids made by the poppy. On the other hand, one of the most successful businesses in the world is supplying those alkaloids at enormous profit. And that business goes on almost entirely unimpeded by the system of rules, which lies underneath it and is less powerful than it. Above the level of the economics and money is biology. An example here of how biology trumps economics, imagine a 17-year-old buying some training shoes. That 17-year-old will spend 200 euros on those training shoes, whereas he or she could equally easily buy a pair for 40 euros that would be functionally just as good. Why according to the rules of classical economics, has that person broken those rules of classical economics? Why have they spent more money on something they need to? The answer is because they're not buying training shoes, they're buying themselves a peacock's tail. In other words, they're performing a biological function rather than an economic function. And of course, above biology is physics. Physics is the substrate on which all of this operates. Nowhere in biology is there a perpetual motion machine. It has never evolved, and the reason that it has never evolved is because physics makes it impossible. The second law of thermodynamics, which is about the most solid physical law that we know about, says that you can't make a perpetual motion machine. So evolution has never hit upon a way of doing that. Of course, the fact that evolution hasn't hit upon something doesn't mean that it is impossible, but in this particular case, that is impossible. Okay, now what I want to do is to look at RepRap, how RepRap works in the context of the first three. I'm not going to say very much about physics. There's a great deal of physics in RepRap, from the non-Newtonian nature of the fluids, the plastic becomes as it melts and so on, the way in which the electronics works, all of that, but I'm not going to be talking about that today. There's an enormous amount of detail about that stuff on the project website. Any of you who are interested can go and look up the physics and the engineering of RepRap. I'm going to look at the first three today. Let's start with the rules. And as far as a home three-dimensional printer is concerned, the system of rules that we have to consider are what are called registered and unregistered rights, things like trademarks and what's called passing off, things like copyright, which is an unregistered right, patent, and registered and unregistered design. I should make the conventional caveat here of I am not a lawyer. However, a lot of what I'm going to tell you about is actually research done by a lawyer, a guy called Simon Bradshaw, and he and I have written a paper on the legal aspects of RepRap and similar machines, which we hope is going to appear in the Edinburgh Law Review. The law here that I'm talking about is the law in the United Kingdom, which is almost identical to the rest of European law. There's a great deal of commonality across the whole of the European Union on how these laws work, but it is different in the United States, and that's an important point. And where I know about differences, I'll mention them, but I may not mention every last one. And let's look at these in detail. Oh, incidentally, as I go along, I should say, on the right or in the bottom of my slides from now on, there'll just be little examples of things made in RepRap machines, which I may or may not comment on as we go through. But if you get bored with what I'm saying, you can at least look at the little object on the bottom right. And that, as you can see, is a little miniature television for an iPod cabinet, television cabinet. Yes. Okay. Trademarks, well, you all know what trademarks are. They're things like Exxon or the shape of a Coca-Cola or whatever written in that curly script. Passing off is the offense in law of selling a fake Rolex watch. It's making it appear that something is manufactured by a famous company when in fact it's not. Now, this is fairly straightforward. If you RepRap something including a trademark, or if you try to pass it off as a product that was made by a famous company, then you are a bad person according to the law. The law is completely straightforward on this. If you fake a trademark or if you fake a product, then that's against the law and that's it. There's really not any great dispute about that. However, there's not a great deal of incentive to do those things. It always seems to me that this, though imitation, as the cliche goes, is the sincerest form of flattery, we as a community should all have the courage of our convictions, and when we make something, say that we made it, not try and pretend that Coca-Cola made it. So I don't think that's a serious restriction on anything that we might want to do. Copyright is a little bit more involved. In particular, the law is not all that well written. If you look at Section 4 of the Appropriate Act in the United Kingdom, it has a definition of sculpture that says sculpture includes a cast or model made for purposes of sculpture, which the philosophers among you will see lacks a certain amount of usefulness as a definition. But what we're talking about here is two possibilities in the three-dimensional objects printed by the machine. Figurines, obviously, if you make a little Mickey Mouse figurine, Maybe Mickey Mouse is copyright by Disney, and so maybe you've infringed their copyright in that figure. Or images on surfaces. If you emboss an image on the surface of something that is copyright, then you've infringed the copyright. And again, the law is fairly clear on that. That's what you've done. But it's important to realize that the right of copyright is actually fairly restricted. So, for example, if you have an industrial prototype, that is not a copyright. So, just to take an example, if you've got a wing mirror for a Ford Focus, that wing mirror is not itself copyright, cannot be. The design documents for it are copyright. In other words, if you go into Ford's main office and you download the file from the geometric modeling program that designed the wing mirror, then that is a copyright file, and if you take that file, then you've broken the copyright. But this is an important point. Making something from a copyright design is not an infringement of that copyright. In other words, the document is copyright. You must not copy the document, but if you use the document to manufacture something, you have not infringed the copyright. So, though the design documents for all sorts of industrial products are copyright, using them is not an infringement of copyright. And if you reverse engineer them yourself and use your reverse engineered version, you have not infringed the copyright in the original document. And there's a famous piece of case law here of the Star Wars knitting patterns. A woman put a set of knitting patterns out on the web for people to knit Darth Vader helmets. There's a Darth Vader helmet made in a RepRap machine. And Lucasfilm tried to sue her for infringement of their copyright in the original drawings they made for Darth Vader's helmet. And the artist who did those for Lucasfilm obviously had copyright in his or her drawings. And they tried to say this woman was infringing their copyright. But in fact, the courts ruled that this was not an infringement because though if she'd made a drawing that was the same, she would have infringed the copyright. Making a knitting pattern to make the three-dimensional object was not an infringement. Another thing that's not widely known about copyright, what is widely known is that copyright extends for an enormous amount of time. I think it's 70 years after the death of the copyright holder or something. But if you're Disney and you allow someone to put Mickey Mouse on a child's pencil case, then the clock starts ticking on the copyright on Mickey Mouse. And 25 years after you first use a design on an industrially distributed product, like a pencil case for a child, then the copyright in that design disappears. So the use of a copyright object in something that's sold in that way actually restricts the time of copyright on it. Patents typically have a 20-year term. And here the exception is, again, completely explicit. Excuse me. If you make something that's patented, but it's for your private, not for gain use, in other words, you make it in your own home, and you just use it yourself and you don't sell it, then you've not infringed the patent. This is one of the locations where the law is different in the United States to the law in Europe. If you use a RepRap machine in the United States to make something that's patented, then you have infringed the patent, even if you're only going to just use it yourself. In Europe, that's perfectly permitted. Another use that's permitted is experimental use. If you make something to experiment with it that's patented, in particular if you're experimenting to try and improve it, then you're allowed to do that. However, the not for gain exemption is not enough on its own. So, for example, if you're a school teacher, you've got a RepRap machine, and you use it to print out test tube racks which happen to be patented for use by your class of school children, then you have infringed the patent, even though you're not using it to make money. Another offense against patent is supplying the means, and this is interesting. What that means is that if you design an object that's patented and you print it yourself, just for your own use, that's fine. If you distribute that design on the web, you're supplying the means to infringe the patent, and you've offended against the patent. Now, there's a limit to how far that offense goes. Pretty clearly, if you sell people screwdrivers, you're supplying them with a means to infringe a patent if the patented object needs a screwdriver to put it together. And the law is not completely stupid. It allows you to sell screwdrivers and lathes, and implicitly, given that it allows you to supply a lathe, because a lathe could be used to make a patented object, and that's not an infringement, the RepRap machine is obviously going to fall under that as well. So the machine itself is not going to be nailed down by people saying this allows us to infringe patents in the same way that anybody can sell photocopiers, for example. And registered and unregistered design, the first thing to say about this is that parts of a machine that's sold by a company that have either registered their design in those parts or just implicitly left the design there but have failed to register it, bits and pieces are only protected if they can be seen in normal use. In other words, anything that's inside the works under the cover cannot be protected by registered design or unregistered design. And there's no protection for technical function. In other words, if a given design achieves a given technical result, then if you do the same technical result by a different design, you haven't infringed the design right. There's also an exception for things that must fit to other things. So if you make a spare part in your RepRap machine for your car, and it has to be a certain shape in order to fit with the rest of the car, then again, you haven't infringed the registered design in the original part made by General Motors or whatever it might be. And finally, the restore appearance exception. If you make that wing mirror for your car in your RepRap machine, the wing mirror housing, and it has to be the same shape as the original wing mirror in order to restore the appearance of the car, then again, even if the original design was registered, you're allowed to do that. So, to summarize all of this, the law, as far as people making things for themselves is concerned, is pretty unrestricted. You can do more or less whatever you like unless you infringe trademark or, in very restricted cases, copyright. Patent doesn't affect you. Registered design doesn't affect you. And because you're not selling anything, you're not guilty of the passing off offense. So people doing things for themselves, the law basically doesn't touch them at all, certainly in Europe. Once you start selling things, then restrictions start to come in on you a little bit more, but even there, things are fairly liberal. Okay, let's chip on to the next thing. Let's look at economics. I mentioned that it costs 350 euros to get all the materials together to make one of these machines. As I speak, the cheapest non-open source 3D printer that you can buy in the world is the SD300 made by Solido, and that costs 12,000 euros. Now, there's a big difference between 12,000 euros and 350 euros. This is actually rather an interesting difference. It's a difference that occurs for a very straightforward reason, and that is that almost all of the 3D printing technologies have been patented, and they've been sold by the patent rights holders up until now, and it's just now that all those patents are starting to come out of their term. However, industry has started dropping the prices a little bit, but not very much. And it's going to be very interesting to see how all the open source 3D printers that are derivatives of RepRap, things like the MakerBot machine, the Bits from Bytes machine, and so on, which are all coming in at really low costs, namely a few hundred euros each, are going to affect the main part of the rapid prototyping industry. Just to give you an example, MakerBot, I should declare an interest here, I own shares in MakerBot. MakerBot make a machine in a laser cutter, which is a derivative of RepRap, but it can't reproduce itself. Though it's an open source design, you can if you've got a laser cutter, you can make one yourself. MakerBot have been trading for less than a year, and they're already selling almost as many machines for much less money, almost as many machines as the top-selling non-open source producer of 3D printers. Almost all the commercial systems are using the Hewlett-Packard ink cartridge strategy as their economic model. You all know how this works. Hewlett-Packard gives you printers, and then they charge you for ink. Sir?
Could you do us all a great big favor and not use the word commercial as opposed to free? Try proprietary.
Proprietary has too many syllables in it, but yes, okay. I'll try to do so. Pick me up every time I do it, but I'll try not to do it. Okay. You all know how the HP cartridge strategy works. HP give you printers and charge you for ink, and they charge you silly prices for ink, and as a consequence, they have a great deal of people with big deal of problems, if they can be called problems, with people making compatible cartridges and so on. All the proprietary, thank you, systems, use the same strategy for the supply of the plastic that you have to put in the machine for it to build things. Typically, if you buy a cartridge for one of the main machines, that would cost about 300 euros, and that contains about 20 euros worth of plastic. And that's a big markup. Of course, with this machine, that strategy cannot work. If somebody tries to put one of these machines out or a variation on it where you need a specific cartridge to operate it, people are just going to design around that, and so that can never happen. Finally, I'm not sure if this quite comes under the heading of economics, but it seemed the best place to put it, the whole idea of home recycling. We all throw away significant quantities of plastic goods, and typically what happens to those is they're put in big containers and shipped overseas for recycling, an enormously wasteful process, even though it's less wasteful than not recycling at all. One of the things that I wanted to do for a little while with this machine is to have the machine make a plastic shredder that you could, for example, feed plastic milk bottles into. It would shred them, and then have the machine have a write head that you can feed those shreddings into, and it would print objects out. And in fact, there's a pair of child shoes that were made out of the same plastic that people make milk bottles out of. And of course, what this means is you can print your child shoes using milk bottles. You've got an entirely local recycling route, no trucks going anywhere. What's more, when your children's feet grow out of the shoes, you just shred the shoes again, shred in another milk bottle, scale the design by 1.1, and you've got a new pair of shoes. One of the key things, of course, about the production of anything is labor costs. And another aspect of economics is the capital you require to start manufacturing something. And as we all know, manufacturing industry is migrating, or indeed has migrated, to China, the Far East, to India, and also to countries like Brazil and so on, where labor costs are low, and that's the reason why manufacturing is going to those locations. However, if you want to start up a factory in China to make digital watches, you still have to invest $100 million in your factory. Of course, in order to set up making things with one of these machines, you only need to invest a few $100s. And what this does is to change the economics of starting to get a foot on the first rung of the ladder to make things. What it means is that if you're a small community in an impoverished area of the world, you don't need $100 million to start a factory to start manufacturing things. You only need a few $100s as that community to start making things, possibly for the use of just your friends around about, nearby to start off with, which would obviously improve their economic well-being in terms of the material goods that are available to them, at least. But then you start selling them, and because your labor costs are even lower in the most impoverished parts of the world than they are even in China and India, then you gain that little bit of advantage as well. Another interesting aspect of the machine is the plastic that, as I say, works best in it, which is this stuff, polylactic acid. You might imagine that you'd be dependent on DuPont or whatever to supply this to you. In fact, you can grow your own. Polylactic acid can be made from starch. So if you've got a few tens of square meters of land where you can grow a starch crop, like corn or potatoes, you've not only got a machine that's self-replicating, you've got a self-replicating supply of the raw material. It's slightly tricky to make in one step. There are 4 steps to making your own polylactic acid from starch. One of them is a difficult one. You have to get it very, very dry. I don't mean you just leave it in the sun to dry out. I mean you've got to get it down to 10 parts per million of water. And that is a little bit tricky. When we've done this in our lab, we've done it by just passing dry nitrogen over it from a cylinder, just an ordinary nitrogen cylinder. That worked. And I conjecture that we haven't tried this, that it should be possible to do it with dry air, made by drying the air through dry calcium chloride. But that's something we haven't tried yet, we need to do. But it's possible to have one of these machines and to be independent of the world's chemical industry for your supply of the polymer that it uses. And all this, of course, tends to make manufacturing much more like agriculture. Agriculture is our oldest industry, and it's entirely concerned with things that copy themselves. That's how agriculture works. Agriculture works by making economic use of things that copy themselves. whether that's cows or wheat. They're all things that copy themselves. This machine copies itself. It makes making stuff in the engineering sense economically much more like agriculture. Okay, let's move on to biology. Now, I've mentioned agriculture. If you've got something that copies itself, it's going to grow exponentially. Of course, it can't grow without limit, but nonetheless, where opportunity exists, it will grow exponentially. So let's take an example, an everyday plastic object, for which many of you got to use, those you can see I don't. Comb on the left. Traditionally, if you want to make one of these, what you do is you buy the machine on the right. It costs you 200,000 euros or whatever. It's an injection molding machine, and you fill it up with nylon, and you make some dies the shape of a comb, and this thing injects the nylon into the dies, and the combs get spat out the bottom. And it makes 10,000, it makes a lot of combs. It makes them fast. It's a really effective process. A very expensive capital cost, but it's a quick process. As I mentioned before, a RepRap machine takes 2.5 days to copy itself. Let's suppose in those 2.5 days that it's got just enough time left to make one pathetic little comb compared with this great machine churning out 10,000 an hour. Now, you all know the power of an exponential growth, so the question is, how many days before the RepRap machines overtake the injection molder? The answer is 20 days. And then the RepRap machines are making more combs than the injection molder. After a month, there's a RepRap machine for every man, woman, and child on the planet. Now, that's not going to happen for the same reason that we're not up to our necks in rabbits. Everything that grows exponentially in number always runs up against resource limitations eventually. Of course, in the case of the machines, it will be places to put them. It'll be whether people want them or not, and it'll be the materials from which to make them, just as it is for living organisms. The reason why we haven't got rabbits up to our necks is because there's not enough grass for them all to eat. What do people do when they get access to things that copy themselves? Well, the answer is they do this sort of trick. They turn those things into those things. I contend that this is actually humanity's most powerful technology. Nothing we've done since the Industrial Revolution touches this for sheer elegance and power. Why is it so powerful? Well, for a number of reasons. The first reason is you don't need to know how any of this works in order to use this technology. You can use this technology if you believe that the sun orbits the Earth. Indeed, most people who have used this technology believe precisely that, historically speaking. It allows you to manipulate matter at the molecular level, the level of DNA, without even knowing what a molecule is. All you need to know to apply this is what you want to end up with. And then the fact that the objects copy themselves does all the rest of the work for you. And of course, one of the reasons, again, why this is such a powerful technology is it's the technology that feeds us all. There are far too many people in the world starving, but we'd all be starving if our as well, we all look fairly well fed, I'm afraid. We'd all be starving if our ancestors hadn't done this with wild grass to make the material that feeds us, either directly in the form of bread or indirectly in the form of the meat that we eat. So that's what people do with things that copy themselves. Of course, as far as RepRap's concerned, people, as soon as the design's out there, start making variations on it. And again, this is just some stuff that I downloaded from Thingiverse when I was putting this talk together. These are all variations on the standard design of the machine that people have posted back on the web. And things that copy themselves are, of course, necessarily subject to Darwin's law of evolution, and there will be random mutations that occasionally happen in the software or the hardware, and those might just conceivably be improvements. But the thing that really drives the evolution of the machine is something much closer to the idea of selective breeding, the thing that we did to turn the wolf into the dogs, in that it's consciously driven by people saying, I want this bit to look like that. And that was what will really drive the evolution of the machine forward. So we've got improvement by breeding. One of the things to note, incidentally, is that old machines can make new designs. I mentioned that Eric's machines over there are the first design that we did. This is the second design. This is my own personal machine that I have at home. I also have a machine at home just like the first design. And all the RepRap parts for this machine were made in my first machine at home. So you've got a new design for the machine, you happen to have an old machine, you can use that old machine to make the latest design. And one of the principles of the project that we're going to stick to is that design N is always going to be manufacturable by design N-1. It may well be that design 10 can't be manufactured by design 1, but there will always be a continuous chain through all the versions of it so that you can get to the latest design from wherever you are. And of course, a slightly stretched biological analogy, this is a little bit like horizontal gene transfer in that you've got old machines acquiring information that's been the product of an evolutionary process and using that information to upgrade themselves. What are the sorts of things that people are going to do to improve the design of the machine? Well, they're going to make it faster. Eric's already working on that. This is really important. Make it simpler for people to put it together. At the moment, you have to be a person rather like all of us in this room to put one of these machines together. Ideally, we'd like to get it to the point where a reasonably technically competent but not technically highly educated person can put the entire machine together and get it working. Make it more accurate. At the moment, it's accurate to about 0.1 of a millimeter. If we can improve that, we can make things more precisely, of course. Fewer added-in parts. I mentioned about half the bits you have to buy externally to put into the machine. We obviously want to reduce that proportion. And indeed, there's a prize now available for $80,000 from the Foresight Institute, just been announced, to improve RepRap, to increase the proportion of parts that it can print itself. So if you want to go out and design a new machine and have a crack at that prize, excellent, go for it. Slightly more abstract biological point. This is really how I came by the idea for the entire machine. I just wanted to spend a few moments talking about it. We're all familiar with the phenomenon that to lay people is called symbiosis. Biologists don't call it symbiosis, they call it mutualism. So let's stick with the technically correct term. Symbiosis, incidentally, just means any relationship between two species. So, for example, lions and antelope have a symbiotic relationship. The antelope probably doesn't appreciate it that much, but they do from a biological perspective. By mutualism, biologists mean a relationship of mutual benefit. And of course, we all know the primary example of this, the one that we're all taught at school, is the relationship between the flowering plants and the insects. This evolved about 130 million years ago in the late Jurassic, and it's been going from strength to strength ever since. And the way it works, of course, is that the flower needs to get its pollen to another flower, but it can't move. So it makes nectar, which is of no use to the plant directly, but the insect values the nectar. The insect visits the plant to gather the nectar, gets pollen deposited on itself, goes to the next plant, the pollen gets transferred. Both species gain a benefit from this relationship. Both of them are happy, and both of them are thereby allowed to survive better than they would otherwise. And of course, human beings take part in many symbiotic relationships. We have a symbiotic relationship with the material that we eat, which may sound a bit like the lion and the antelope, except some of these species are incredibly successful as a consequence of this symbiosis. For example, corn. If we look at it from the corn's perspective, corn has managed to enslave another species, get it to clear vast tracts of land for the benefit of the corn. When the corn gets sick, we go to the nearest spaceport, we throw a satellite into orbit, we take its photograph, we fly over it and distribute drugs to make it better. At the end of the season, we gather a sample of its children away and store them most carefully in cold, dry conditions so that it can get a head start the next. We don't do this for our own children, for heaven's sake. So the corn just has to sit there and grow. Chickens are the most successful bird in evolutionary history in terms of numbers. There are 15 billion chickens on Earth. And the reason for that is simply because they have a symbiotic relationship with the most powerful organism that has ever lived. And of course, flour and eggs together make cake. And so we've got a direct analogy here. We get the cake, and the corn and the chickens get to reproduce preferentially. Oh, right, I've got to get on. Time's up. Anyway, a mutual evolutionary stable strategy is what's been established by the flowers and insects, and it's a stable Nash equilibrium. RepRap is the same in that the machine is equivalent to the flowers, the people are the equivalent to the insects, and the goods that the machine make, that the people value, is the equivalent to the nectar. And so it seemed to me that the machine ought to have a stable relationship with human beings in exactly the same way as the flowers and insects have a stable relationship. We all know that's the wrong way round. The arrow of time actually goes the other way, of course. Instinctively, we know that from our intuitive feeling for entropy. However, occasionally the arrow of time appears to go backwards, and of course it's evolution that drives that process, and it does so by expending energy, so it doesn't break the laws of thermodynamics, in fact. Everything on the left gets replaced by the stuff on the right. You can all remember, I'm sure, buying photographic film in rolls. I bet none of you can remember, well, one or two of you probably can remember the last time you bought a roll of photographic film. There'll be usually a show of 4 hands at the moment of nutters who still use film. But there we go. Okay, what of the future? Well, you all run your own CD pressing plant, your own photographic lab, and your own printing press. And of course you do it all courtesy of these devices. Why shouldn't you run your own factory that makes more factories? That's all I've got to say. There's the website if you want to have a look. Thank you very much indeed. How long have we got for questions? Or any jump? A couple of minutes? Okay. Yeah, if anyone's got a question. Yep. Oh, right. Sorry, I stand corrected. Clearly, they must really exist, and the second law of thermodynamics is nonsense, as demonstrated by eBay. Anyone else? Sorry, louder. Yep. Well, there are 2 ways we can go about printing PCBs. We're not quite... sorry, for everybody else's benefit, he said, what about other materials, in particular printing PCBs? There are 2 ways we think that there might be possible to make PCBs. One is a fairly obvious way of putting a cutting head in the machine and milling the PCBs, and I've actually got a design for that, which I haven't finished. I need to get on with it, that will use a Dremel and the flexible extension cable you can get with the Dremel to allow you to mill a PCB in the machine. That would make a conventional PCB, and that should work fairly straightforwardly, I think. The other and more interesting way is to have a material that's electrically conductive and to deposit that with a machine. And in fact, I've just taken on a research student to work on precisely that problem and other problems. He's already got several conducting pastes, and he's got the design for a paste extruder that was based on the paste extruder called the Frostruder that the MakerBot guys did. And so we'll be putting those together in the fairly near future. Whether they actually allow us to make a PCB that works is something that'll be interesting to see. But
are you planning to hold any events this year to help people build RepRap?
Not me personally, but there are a number that are going on. I'm afraid that my time is pretty much occupied by running the project and developing the machine and coming to events like this, for which thank you again. So there will be several. For example, I know a university in Scotland that is running a series of courses on building these machines for school teachers. So there are lots of events like that that other people are organizing.
Since the machine builds objects in layers, what are the physical limitations on the kind of objects that you can make?
Well, the principal limitation is the resolution of the machine. I mentioned that it's accurate to 0.1 of a millimeter. That's in the X and Y, the horizontal plane. You can set the thickness of the layers, but typically the thickness that we use to build most objects is 0.3 of a millimeter. So it's actually rather coarser in the vertical direction than the horizontal direction. Now, that's okay for making most parts, but it's not, for example, as accurate as a conventional machine tool that cuts metal. That will be 10 times more accurate than this machine. So that's one aspect of the limitation. The other is, at the moment, the machine works with thermoplastics, We are fairly sure that we can move it, indeed we're designing a head changer so the machine can swap heads and work with different materials inside itself automatically. We can move it so it'll work with any material that's a paste at room temperature. So it'll be things like ceramic slip, for example. We'll be able to make objects in ceramic slip which you'll then be able to fire in a kiln, and you'll then have a refractory object that will withstand high temperatures. The conducting pastes I already mentioned in response to the previous question. Another material that will work quite well in the machine, we know this from the Fab at Home project, is silicone rubber. You can extrude that as a paste and build flexible objects with it. And that's actually rather useful because you can make objects that are rigid in one area and flexible in another area. So you've got a single entity which has a built-in hinge or whatever it might be, or a built-in spring. And that's very useful. The other thing you can do with silicon very usefully is to make seals, which are either water or gas type. So that'll be convenient as well.
What are you doing to improve the resolution?
No. Well, the short answer to your question is I'm not doing anything to improve the resolution because it's good enough for me. But I would love to encourage the community to improve the resolution. There are a number of different ways you could go about doing it. You mentioned feedback. You could certainly put servos in place of the stepper motors, and then the resolution of the machine would depend upon the PID control you did on the servos and the measuring device that you use for measuring the linear movement. You can certainly get very accurate magnetic rotary encoders now. From a company in Austria. You can get rotary encoders that will do 4,096 steps per revolution, for example, and that would allow us to make a very accurate machine indeed if we incorporated those into it.